Viewed globally, prime numbers follow strict laws. We can predict their density over large ranges with high precision. But as we zoom in, that order vanishes into a scattered, chaotic arrangement of points. Locally, they appear as independent random events. For centuries, mathematicians have attempted to find a logic behind this local unpredictability. Knowing the location of one prime tells us almost nothing about where the next one will appear. In 1859, Bernhard Riemann introduced a new way to measure these irregularities. His work on the zeta function provided a tool to describe the fluctuations, the wobbles, in how primes are distributed. Even with Riemann's insights, the scientific consensus remained unchanged. Primes were seen as fundamentally random occurrences, like a sequence of coin flips, with a local distribution that was essentially unknowable. This is the classical assumption of the last 160 years. Primes are the source code, the physical events, and the zeta zeros are the statistical byproduct used to filter out their noise. But there is a possibility that our understanding of this cause and effect relationship is backward. A new hypothesis suggests that the zeta spectrum is the foundational environment, and that prime numbers are the resulting patterns of that environment. If we use the metaphor of light and shadow, primes are not the glowing source. They are the shadows cast by a hidden, deeper frequency. If this perspective is accurate, we should be able to map this frequency and identify exactly where prime numbers are mathematically expected to cluster. Finding this frequency requires us to stop feeling primes as isolated points on a standard number line. Instead, we translate the Chebyshev fluctuation into log space, viewing prime distribution as a continuous, oscillating wave. Within it, a dominant, low-frequency oscillation stretches across the dataset. But amplitude, the height of these peaks, isn't enough. Primes don't always sit at the wave's highest point. To find them, we have to look past the size of the oscillation and measure its rhythm, the underlying angle of the wave. Predicting prime behavior requires treating the numbers like a noisy audio signal, shifting the focus from amplitude to phase. Using a Hilbert transform, we can extract the phase, a latent state that dictates the timing and rhythm of the oscillation. This phase is built directly from the frequencies of the Riemann zeta zeros. Mapping this spectral phase creates a regime diagram of distinct zones, areas where primes are mathematically favored to cluster and where they are sparse. This map looks ahead to predict future prime density intervals successfully, using no previous prime numbers, relying entirely on the phase state. This successful prediction suggests that primes are not random occurrences, but events conditioned by this hidden phase environment. Statistically, this behavior categorizes primes as a Cox process. A Cox process is a driven stochastic system. In this model, events are not independent. They are governed by a fluctuating background environment that constantly shifts the underlying odds of an event occurring. Primes are reacting to a complex interference pattern created by many intersecting zeta frequencies. They are events responding to a mathematical topography, rather than the objects creating that topography themselves. This aligns directly with the Hilbert-Pullier conjecture, which suggested that a hidden geometric operator might be responsible for the primes. The data suggests a final shift in perspective. The spectral frequencies are the light source, and the primes are the shadow. Prime numbers do not generate the rules of the mathematical universe. They trace the outlines of a structure that already exists. What we once saw as a chaotic distribution is actually the physical manifestation of a hidden universal resonance.